Thank you very much, Jerry, for inviting me to this talk. I have learned so much, and what I'm going to present to you, I hope it's also going to be a new way of learning, of looking at what other people thought it was. Everything we knew, it was settled. But every time we have to learn from new. And also I learned that there are heroes. I like that word, because we need people to inspire us. And I think today we have, in this conference, we have been inspired. My personal heroes, I had the pleasure of meeting Jacques Benveniste personally. And of course, you know some people here. And also Dr. Batman Jelic. He's a doctor, he's Iranian, and he's trying to show us that the chronic dehydration is the most important disease. And if we treat that, everything will be treated. Also, I know personally Dr. Arturo Solis Herrera. He's the developer of this theory of photosynthesis in human and animals. So it's very interesting. But there is another hero that nobody talks about, and has to do with pH. The reason is because he died. Yeah. Of course, we have Albert St. Georgi. Yeah. Peter Stewart, what he was a Canadian physiologist, and he studied physics and mathematics, and then later did a PhD in biophysics, and taught physiology at the Emory University. And he developed a quantitative model of acid-base, which is very, very different from the qualitative model that we have been used to. And so, trying to recover his teachings, he died in 1993, we have learned a lot of things. So, normally a theory needs like 30 years to get established. So if this theory was established in 1981, well, the 30 years have come to an end, and so we need to improve on this theory. So acids and bases are part of our daily life, but there are many questions that we have to ask. What is an acid? What is an alkaline? What is a diet that produces acidity or alkalinity in our bodies? Yeah, what are the biological limits? And what is the biologically apt pH for our blood and our cells, which is very different. You know that pH in blood has to be 7.4, but the cell can easily go down to 6.2. So why is it possible that the cell can endure so much acidity? It's not so much, really. Okay, what do we know about acids? From our everyday experience, we know that acids change the color of some dyes, that it has a specific taste that reacts with metals. On the other side, bases are slippery to the feel and also reacts with acids to form salts. But what about the profound physiological knowledge? Well, these theories have evolved during the ages. One of the first was Paracelsus, who said that, well, he discovered hydrogen because once an acid acted upon a metal, he discovered a gas going out. Then you have Robert Boyle that talked about tiny, pointy corpuscles that like sting to the tongue. And then Antoine Lavoisier, he changed the whole thing, said an acid has to contain oxygen, because oxygen, if you see what the word means, it means acid forming. Then Humphrey David said, no, wait, it's not oxygen, it has to do with the hydrogen. And then also Dulong said there has to be an electronegative compound and an electropositive compound, which is the hydrogen. Then Berzelius said, no, wait a second, it's the oxides of metalloids that once you are poured into a water, they develop an acid. And again, Justus von Liebig said, no, wait a second, it has to contain a hydrogen atom. And as you can see, theories have gone back and forth between what is an acid? Is it something that contains a hydrogen, or is it something that contains oxygen? Our modern history of acids starts with Arrhenius, and he said an acid is a substance which forms hydrogen ions, and also talks about water splitting, water dissociating. Profesir-Investigador in 1923 said an acid is a proton donor and then a base is a proton acceptor. And then Lewis same year said, no, wait a second, an acid is an electron acceptor and a base is an electron donor. So who's right here? Yeah? And does these definitions really help us to understand acids? For me, it has been quite complicated. I haven't really understood Profesir-Investigador. For example, what does he say? Okay, an acid, like here a carbonic acid, and water is a base, so you have a conjugated acid and a conjugated base. So here water acts like a base. But then you have another example where you have bicarbonate is the base and the water is the acid. So what is really an acid? What is really a base? Yeah. Then we have the concept of pH. pH, yeah, it's the negative logarithm of the concentration of hydrogen ions. And pH was introduced in order that we could make sense of huge differences in levels of concentration. And if you tell me, is this normal? No. Look, I'll give you a very small example. Imagine that we are going to make a walk, yeah? And that walk takes distance. And that distance, we're going to make it in meters. Let's say that 10 to the minus 14, it's 1 millimeter, yeah? So if I take one step of 1 meter, in what pH I am at? If I started at pH 14, and I take 1 meter, and taking that 10 to the minus 14 was 1 millimeter, I jump from 14 to pH 11 in one step. That's 1,000. And then for each step, it goes 10 times more. So second step is 10 meters. Third step would be 100 meters. Then next step is 1 kilometer. And then 10,000 meters, 10 kilometers. And so we go on. By the time we arrive at pH 1, it's like having gone to Mars and back. You know? And can we understand those distances? Can we understand those concepts? It's very difficult. So normally I never use the pH concept. I use hydrogen ion concentration to understand it. Yeah? And so the question bears, is it really necessary to produce a new paradigm about acid-base theories and acid-base balance in the body? What happened? Classical theories, you see the timing. 1887, 1909, then the Henderson-Hasselbalch equation is from 1916. Then we have the two theories, the actual two theories from today, 1923. Are they still actual? Are they still representing the most advanced levels of science? Or are there any new theories? For example, this general definition of solvents was produced by German in 1925 because he wanted to correct the things that he didn't think it was correct here in these previous theories. And then Stewart takes this theory and it produces a new advancement in science. Also, we have to see the way we use acids, it has to do with, is it really working the way we use these concepts? For example, in medicine, we know that there are strong acids and bases. We know that the partial pressure of CO2 produces acidity in the patient. We know that we have a buffer system in the body, but are we really using that to cure patients, or are we using those old theories to produce iatrogenic disease? Yeah? And at the end, we have this equation, Henderson-Hasselbalch, which only uses one variable, and the question is it really helpful? Are we in a qualitative or a quantitative theory? And my idea is that we have to jump to the quantitative. So where do we start? We have to start with something, and that something has to be the most basic level of knowledge, which is the biophysics of water. And water, it's not H2O, as we have seen. Water, it's very complicated. It behaves like a crystal, it behaves like a complex, like a matrix. Yeah? And then you have these protons that go jumping from one water cluster to the other, and that makes it very difficult to say, okay, I have a proton. Is it possible to have a proton in your hand and manipulate that proton? No, it's impossible. That proton has a 10 to the minus 11 second life. So what we have is a very complex system. We shouldn't talk about water, we should talk about systems, because in that water we're going to dissolve solids and gases and stuff. Yeah? Also, water is very concentrated of H2O, it's a solution. Yeah? So when we talk about water, we have to see the complexity. And the first thing they teach us at school is that water ionizes and water splits, and we have, from one water molecule, we have one hydroxyl ion and one hydrogen ion. Yeah? But is it really true? Mostly this proton, what it does, it's going to stick to other water molecules and become the hydronium ion, more or less, pardon, and it does this, no? So water splits, one proton goes to another water molecule, and so we have two ions, the positively charged and the negatively charged. But then we go to more complex systems, like for example, when we put a solid, and in this case it's acetic acid, the acetic acid has to dissociate, and where does this proton go? It will go to a water molecule, and then this water molecule will change. Now we have an anion and a positive ion here. Next thing is that we have to always see that the charge in water has to be maintained. Here we have the same, let's say that this molecule is the green one here, just for simplicity. And what happens to this proton? Well, the proton dissociates, but it gets stuck with the water surrounding the same molecule. So where is the proton? The proton, actually, it's like hidden, but another proton is jumping from one side to another. And here we have protonic jumps that you see. At the end, we have this phenomenon. For each negative charge here, because this water cluster here is charged negatively, we will have a proton being free. And we have crystals, and those crystals are neutral. Yeah? So for each negative charge, we have to have a positive charge. But that charge is not always the same. It's always jumping, it's always changing. Sorry for the Spanish. Okay. In this new theory, general definitions of solvents, we have definitions of what is the cation of water, it's called leonium. What is the anion of water? It's called leate. And an acid is that substance that increments the concentration of the leonium ion and reduces the concentration of the leate. Yeah, so an acid is part of the system, it's not a thing, it's the formation of acidity that we're talking about. And the base is the same thing, only the other way around. The base increases the leate ion and decreases the leonium ion concentration. So in water is not always a solvent, but in biology we'll take it as a fact. So acid is any negative charge that produces a major dissociation of water and increases the concentration of protons. And the other way around, the base is any positive charge that produces a major dissociation of water and increases the concentration of hydroxyl ions. So in that way, it's very simple. Is it a negative charge? It's an acid. It's a positive charge? It's a base. That's it. Nothing more to say. Well, now it comes the complicated part. Because Stewart didn't stop there. He said, okay, let us see what's in the blood. Look, this is your blood. You have cations, strong cations, for example, sodium, potassium, calcium, magnesium. Then you have strong anions, sulfates, chlorine. Yeah, those are always dissociated. And then you have the partial pressure of CO2. And that will produce carbonic acid and bicarbonate and carbonate, and then you have weak anions, and then you have a lot of other stuff. How can you predict the pH of a patient if you have all this mess? It's impossible. And then you only have Henderson-Hasselbalch equation, which can only handle one variable at a time. Yeah? And so what he did is, well, let's organize this, and from all this, he said there are only 3 independent variables, and these independent variables are going to change the dependent variables. So my independent variables are strong ion difference, the partial pressure of CO2, and the total of weak anions. Yeah? And then he uses a system of simultaneous equations, and he gets this. But before we go to this, we have to check the laws of chemistry that that has to be taken into account. Yeah? But here I have my independent variables, the laws of chemistry, and the dependent variables. Look, bicarbonate is here, and this we will talk again. So we have our 3 theory laws. What is the first law? The first law of principle of electron neutrality of water says that the sum of all charges has to be 0. So when I graph this, I will have a gamblogram where I split the charges in cations and anions, and this has to be exactly the same. If not, something went wrong with the mathematics. And the question is, how is it possible that different solutes produce always a negative, neutral charge in the water? Well, because we have water ions here, the proton, and here the hydroxyl ion, which are constantly growing and decreasing in order to maintain this electron neutrality. So if I increase sodium, which would be here the blue one, yeah, on this side something would have to increase, and that something would be the hydroxyl anion. On the other hand, if I increase here the chlorine anions, something has to increase here, and that would be more hydrogen ions. So water is always regulating itself, and it's always water that is donating and accepting the protons or the hydroxyl ions. Then we have the second law. It's the law of mass action, which says any reaction eventually reaches equilibrium, and once we know the equilibrium, we can see how it's going to react in the reaction. And then we have the law of mass conservation. This is very important because in Stewart's law, we don't care if it's dissociated or not dissociated, that acid. It's the total of acids that we're looking for. Why can it dissociate? Because the medium produces the dissociation. Why does it reassociate? Because it's the medium that does it. And then, okay, we have this 3 variables, which are our strong cations and anions. We have the partial pressure of CO2, which produces carbonic acid, bicarbonate, and carbonate. And then we have the total amount of an anion, which can be protonated or not protonated. We also have to know the temperature of the medium, which affects the system. And we have to draw our equations. These are the 6 simultaneous equations that Stewart established, and all these 5 equations can be put here into the 6th equation or the 10th equation, yeah, so that we have electron neutrality. At the end, what do we have? We have an equation with lots of constants, which we know them. These are textbooks, maybe we should revise them. But then we have everything that we need to calculate the pH. It can be done through a polynomial equation, or it can be done just by searching for the most probable hydrogen ion concentration number that will give us finally a 0 value. So this was done for basic. Everything is in the presentation if you want to later check it. Or you can cheat, like I do, and have a software that does all the work for you. This is from Phil Watson from University of South Carolina, very nice software. What you do is you put your independent variables here, you put the partial pressure of CO2, you take your albumin values. Phil Watson also checked how phosphates work in this as a system, the temperature, and you calculate and you get the values in a ganglogram. Why is this important? Well, the thing is, for any patient at any time we can put the variables and get a correct value of pH. Is this important? Absolutely, because if that patient has acidosis, I need to correct it, but where is the acidosis? Which of the variables is out of range? And that's the job of the doctor. We need to correct the pH in the body. And also, remember, the body has many compartments, so every compartment would have to have an analysis. Well, this is an Excel spreadsheet I made myself. So in this case, for example, I don't just want to know the moment, I want to know the pattern. So I can, for example, I just did 24 hours. And so I have a curve that tells me how is the patient changing its pH during the day. And always I have to check my ganglogram to see if it's correctly balanced and where are the most important ions, and both cations and anions. So, okay. Just assume that this theory is the correct one and this theory supersedes and goes against the other one, because one thing I have to say is there's no way of using both theories at the same time. Either Bernstein law is correct or Stewart is correct, but there is no way, chemically speaking, that both theories are correct. So we have to choose. The big advantage we have with Stewart is it is quantitative and it has been mathematically and chemically proven. Okay, so there are many assumptions that we would like to check. So, are there free living protons? Stewart's theory says there are none. They are all stick to some other water molecules. The bicarbonate ion, it's not a buffer, it's not a base, it's an acid. The bicarbonate ions are volatile, so you cannot inject them, they will change. And they have an effect on easy water. Yeah? So this is taken from Jerry's book. And what we have here is just a comproval that when you put charge in water, you change the pH. How do you do that? Just take a battery and put the positive side on one side, the negative on the other, and on the positive side you will have a lowering of the pH, and the negative, where you have more electrons, you have an increase in the pH. Of course, Jerry is later using this as a battery. Yeah. But then you have changes, and we see this here, the Naphthalene layer, and then we see the easy water, and then you see a huge, let's say, acidic layer of water, which goes diminishing in its concentration as it goes further away. Why is this? Well, there are many questions I have. For example, Naphthalene is a negatively charged surface, so it will have to produce a positive water somewhere, and this is a positive water. Yeah, the concentration also changes. The more microspheres we put, the more pH changes we will see. So I cannot say we know everything, and after this conference I can say I know nothing about water. Everything has changed. But what I can say is, yeah, there is an increase in protons, but how do we explain it? I have no idea, really. Okay, these protons erode the easy water formation, so this is very important, because what we are doing in biology is to maintain easy structure. This is so important, and any change in pH will affect this structure, and then it will affect the membrane, it will affect the proteins, will affect the reaction. And if you tell me why is a change in pH so life-threatening, it might be because it erodes the EC layer. And that Look, the changes are minuscule, but the effects on the health is major. The other thing we said is there are no free-living protons, because imagine that what is a proton? A proton is a very, very tiny stuff made of 3 quarks, and it has a diameter of 10 to the 15 meters. In comparison to the atom of hydrogen is huge, yeah? Meaning 10 to the minus 10 meters, 1 angstrom. So what's the big difference? Well, imagine that one proton is the size of a 1 meter balloon, very orange, yeah, very bright. And you release that in Varna, or the atom would be like 100 kilometers in every direction. So that's so tiny, it's a proton. So there are no living protons up there. But most of biological hypotheses were based on the existence of a free living proton, like Mitchell's chemiosmotic hypothesis. It cannot be correct. So here, for example, we see this textbook example where we have protons being pumped into the intermembrane space of the mitochondria. How is it possible that a proton exists free living? You need to have a negatively charged producing that proton. So my idea is something is changing in this membrane, or something is changing in this protein, or an anion is being pumped. But there is no possible way that protons are accumulated here and that they are driving the ATP synthesis. The other assumption is, what about bicarbonate? Bicarbonate is not a buffer. Here you have the bicarbonate ion, and depending on where it is, it will go to the left or go to the right, and that's why they say, oh, it's a buffer. But no, bicarbonate is an acid, and it's an acid with a pKa of 6.1, so it's a weak acid, but it's reducing the pH of the cell, and that's why we have to eliminate it constantly. So, but then they say, okay, in all experiments I put bicarbonate and the solution increases in pH. Everybody has seen it. Well, it's not the bicarbonate that did that, it's the sodium. Because remember, you are putting sodium bicarbonate into the solution. As well, you're putting sodium bicarbonate into the patient. It's the sodium. And this is my other grudge against the medical establishment. They have this crazy idea that sodium is a bad guy. No, sodium is not the bad guy. Maybe chlorine, but not sodium. Yeah. And so the Henderson-Hasselbalch equation took the bicarbonate into consideration and put it here as it were an independent variable, when in fact it's a dependent variable. It depends on the pH, but the pH affects, and so this is a circular relationship, and what it does is leads us nowhere. So Henderson-Hasselbalch cannot be used in this sense. Yeah. And what about pumping bicarbonate ions in and out of a cell or organelle or membrane? It's not possible. Yeah? Bicarbonate will change depending on the pH, so you cannot pump it. What you have is a passage of CO2 from one compartment to the other. Yeah? Okay. I just want to show you a graph, the application. Look, what about fluid therapy in a patient? When did this start? The first patient was like in 1667, got a blood transfusion from a dog, and the guy died, obviously. But then from then on, they were improving on the intravenous treatment of patients. And as you can see, well, lots of things were done in the 19th century. But then somebody said, what is the concentration of sodium chloride in blood? And he came with a number. This was Hamburger in 1882, and the number was 0.9% sodium chloride. And it's wrong. Yeah, in reality is 0.6%, and the other 0.3% of sodium it's attached to another thing, but not to chlorine. So what's the problem? That we continue with this like paradigm that every solution has to be 0.9%, and it's wrong, and it's causing lots of problems with the patients. Yeah. So this is, we continue a development of treatments, of solutions, yeah, but all based on the saline solution, and it's wrong. Yeah. For example, here we have a comparison of different saline solutions. Saline solution has 154 milliequivalents of sodium and 154 milliequivalents of chlorine. But urea plasma has 140 and only 105, 107 of chlorine. So the excess of this chlorine will have a diminishing effect in the pH, so it's acidifying. All solutions, you can see, starting from a 7.4, diminish the pH, all of them. Why? Because they have too much chlorine and too little sodium. So we have to change the idea that an acid is only that molecule that has a proton that can be donated. No, an acid is any negatively charged particle that enters the water system and produces deprotonization of the water and acidity. So chlorine is the bad guy. Yeah. So, but blood is one thing, then we have interstitial space, then we have intracellular space, and each one has different ion concentrations. What is the concentration of sodium in blood? Very high. What is the sodium concentration in cell? Very, very low. Why is this? If you see the major cation in cell, it's potassium. And that question is one of the most important questions in biology and physical chemistry. Why is the cell almost depleted of sodium and very high in potassium? And it has to have something to do with EC. Yeah? How many layers of water surround the sodium? Lots of them. So it's the hydrated ion is so huge it cannot enter the cell. But the potassium ion, which is bigger, hydrates with less spheres, with less water, and then its hydrated radius is very small and it can enter and leave the cell easily. The same happens with other stuff. But now we know why sodium is outside the cell and potassium is inside. It has to do with EC water. Also, plasma, urine, for example, we always say, oh, we need to eliminate acidity from the body, and the urine does this, but how does it do it? Yeah, the prevailing theory is that it does it by producing bicarbonate and eliminating a proton. No. What it does is it's extruding the ions and then reabsorbing some of those ions. And those ions that are not absorbed, that are finally eliminated, are the ones that acidify the urine. Those ions were in your body, now you have to eliminate it. If you look at here, yes. So the reabsorption is very high here, but sulfates and phosphates have a very low reabsorption rate. So when we are eliminating acidity from the body, it's because we're eliminating sulfates and phosphates, and there was a talk about the dangers of too much sulfates in the blood and a bad sulfur metabolism. Well, that's the reason. It's very acid forming. Okay, so to finish this, I just want to show you that we can do quantitative acid-base analysis. This is what I do with patients. I check 24 hours a day and see how they change the PCO2, how they change the strong ion difference, how they change the albumin, and how does these changes here affect the pH. And the model is so good, we only have like 5% error, but it can help any doctor to say, on the bedside, say, what is the pH of my patient? Just check the ions. And if you check the ions, you will see not only the pH, but what do you have to change. Okay, well, that would be it. And here is the bibliography for this talk. It's Stewart, 1981, 1983. I did my PhD thesis with Stewart's theory. And, well, this is my email in case anyone has questions or wants to keep in touch with us. Yeah, well, that would be...
Thank you. Thank you for your really interesting presentation. So one of the things that caught me is regarding the acid having a negative charge and the base positive. So, but we have an observation that I would think doesn't seem to go with that. We put an acid in a beaker and a base, a strong acid and a strong base. We used a voltmeter and we had a little salt bridge between them so current could flow. And we found that the acid, the potential difference between the acid and the base was, I think, a volt or something. It was really big, and the acid was the positive one, and the base was the negative one. Is that, I mean, would you...
Yeah, when you mean acid, which one was it?
If I remember, it was concentrated sulfuric acid and concentrated sodium hydroxide.
Yeah.
Maybe it was a volt and a half even, I can't remember the magnitude, but it was a very big potential difference. And also, you know, we've handled...
Yeah, well, let me explain this. If you put, somebody has to... Okay. If you put like sulfuric acid in that, yeah, what it's going to happen is that it's going to draw lots of protons, and that will change to the positive side. And on the other side, you put the sodium hydroxide, it will draw hydroxyl ions, and it will record a negative value. But remember, what we're looking at is change the name acid. Sulfuric acid or sulfates, what it does is acidify the medium. So it's a system that has become acid. I don't talk about acids in the same way as other people do. We talk about the acid-forming anions and base or alkaline-forming cations.
The last question, I'm afraid.
Hi, thanks. I've been in quite a few clinical situations where you're giving a lot of normal saline to patients, and you know, from what you're saying, that we've got normal saline so long, then I'd expect there to be more of a change in the blood urea and electrolytes, and also in the blood gases. But you don't see that. Do you think we're not measuring it correctly in some way?
Yep. For example, most of the work I did in hospitals, nobody was measuring chlorine ions. Nobody. And what happens very much is you take the blood sample from the subclavian R3, you put it in the gasometer, and the gasometer has been prepared to measure sodium, potassium, calcium, phosphates, but never chlorine, because the doctor doesn't think the chlorine has anything to do with acidity. But what we see is that you increase the chlorine, and what it does is makes the whole body react, and the kidneys start flushing that chlorine out of the body, and that's why you don't see so much damage, because the patient, it's compensating. But in a patient that has several damage, either lungs, kidney, gastroenteric tract, it will show. Yeah? And there is published evidence that saline solution is really affecting the patients. The thing is, we have to change the way we see it.
Thank you again.